But
Charles, if we have about half an hour, I think it would be good to run through some examples and with putting errors in the .cfg files to give people an idea of what error message they see and how to diagnose.
Okay, in the 3D hexade examples?
Yeah.
Okay.
So do things like misspell the names of components.
Okay. What if we do just, what happens if we just do is there missing information that's in the Green's function file that we won't get? We'll find out in a minute here. My computer's been slow. Boy, that's stuff. Maybe I'll quit out of extra stuff. So here we have one right here. So what happened here? Yeah, we're missing information. So we didn't get a spatial database because the default fault type would be fault cohesive kinetic. But we're not using that for the Green's function problem. And so that additional information is specified in the Green's functions.config file right here.
Can you walk them through that backtrace?
Okay. So, all right. So we start at the top. We're going back.
I'm talking about the backtrace at the bottom.
Right, take trace from the bottom. So compile it out. What we have is it's within time-dependent problem. The specific thing within there is our interfaces. The specific thing within there is our fault. And specifically, fault cohesive kinetic. And what that's our first clue that something is wrong, because what you might say is, wait a minute, this is supposed to be, we're supposed to be applying impulses. This is not fault cohesive kinetic. And then it continues through, because it thinks it's a fault cohesive kinetic problem. It goes through the different components of that: earthquake sources, single rupture, kinetic source, split function, the step split function, split simple database, and then the thing that you see is that, oh, there's a database that wasn't provided. And so that means that the database that tells you the slip was not given. So that's the problem there. And the reason is because it thinks that we're using fault cohesive kinetic fault type. And we did that by not giving it the right problem type. So that's right here at the very beginning. If we had, then it would have run as we did earlier. So let's see. What if should we play with that's in step 03. That one has a fault, right? Yes. What if we did something similar? Okay, and what if we left out the spatial database in this? case. Yes. Okay. Now we've got a similar type of trace. It actually looks very similar. So we have highlight out. The problem is time dependent, which is correct in this case. So the problem is in our interfaces within our fault cohesive kinetic, single rupture, slip function. The default slip function is a step. And then it has to know where to get the slip. And so it's expecting a simple IOSCII database, but we didn't give it one. So this error actually looks very similar to the one we just had, but in this case we know that it actually is a time-dependent problem and that it's cohesive kinetic fault type. So it's like now we have to look and figure out, well, why didn't it get the spatial database? So, and there we go. We didn't get it. Now here's one that happens sometimes. If we run this with no label attached to the, there we go. So in this case, similar error message all the way back through, but in this case, we did not provide a descriptive label for our spatial database. Now, in old versions of Pilot, this didn't used to be an error, but we've gotten stricter, and the reason is because it actually helps quite a bit with being able to resolve problems. So if you can give a label to all of the different the things that require a label, then it's easier to trace problems. So if we finally go back and fix that, this should run okay now. Okay, and so there we go. Let's see. I'm trying to think of another one that would be good to mess up.
Mess up a spatial database file.
Oh, okay. So, okay, that was using probably Mat Elastic, wasn't it?
I only think we have one data point. So look at this, maybe the slip.
Final slip?
Yeah.
Okay. Oh, okay. So we're going to tell it that we have, 4 values, when in reality, there's only 3. So maybe, yes, we did get a problem. Okay. Error occurred while reading spatial database file, spatial.db, final slip.spatial.db. And it could not parse the unit string because we told it the wrong number of values. So oops. We can fix that.
We have
we can get
question, Charles.
Yes.
How to add a viscoelastic? So replace the lower crust elastic block with a viscoelastic block.
Okay, that's actually one of the examples. Let's see. Okay, where's the first one that has?
Step 7 has it, I think.
Okay. So here's our, here we go. So in that case, what we do, we've changed materials.lower crust, and instead of what we assigned in pilotapp.config, which is actually also the default is elastic isotropic 3D. And instead, we're going to change it to Maxwell isotropic 3D. Now, once you do that, you have to tell it where to get the material properties because it requires more properties. So that's what we're doing right here. We're saying that this is a file name that contains the material properties for a Maxwell viscoelastic material. And here we're telling, then we're also going to have it output these. So the things that are computed, yeah, these are the computed values. What we'll do is we'll look at that spatial database. We go to so here is what it looks like. It looks a lot like the mat elastic. The difference is that we've now added on the viscosity parameter. So you have your density the same as before, Vs, Vp, and then viscosity with units of Pascal seconds. And so then all you have to do, this is just uniform properties. So density, Vs, Vp, and then your viscosity value. So it's fairly straightforward, and it's similar. There are some other examples that have different types, like we were just looking. Let's see. This one here, step 08 does the same thing, but in this case we're using power law viscoelastic material. And then we have another one that does Drucker-Prager elastoplastic. So does that answer that? I could run it. Did I see another comment there?
I don't think at this time we don't have any more questions, but keep them coming if you do have questions.
Yeah. I'm trying to think if it's good to do another messed up example or to run one of these examples just to see what the results look like. Let's see. Let's typing.
Aaron requests running another example.
Okay. How about the one we just looked at, step 07?
We did step 07 and schedule A yesterday.
Well, why don't I do a different one then? Why don't I? Well, I could do the one with power law. It'll take a little longer to run because it's nonlinear. Let's see how my computer's doing. So this, okay, that was just a warning that was not. So when we do this, you actually need to run several iterations per time step because we're now solving a nonlinear problem. I guess we could look at the, but we're going to cover that, aren't we, in a later, we're going to cover SNES stuff?
We're going to cover that a little bit. So we're going to cover friction in session 5. We're going to cover SNES in later today in session 4. Yeah. So you could do like a Neumann time-dependent boundary condition.
Yeah. Oh, okay. Well, I just ran step 08. And the thing that it used there that was not being used previously are the nonlinear solution stuff. And this is the PET-C nonlinear solver. And it's somewhat analogous to the linear solver, but you give it the relative tolerance for the nonlinear solution convergence, an absolute tolerance, the maximum number of nonlinear iterations. We're telling it we want to monitor the solution, and then we're not actually using the line search in this, I don't think, so that's not. But then you want it to tell you whether it converges, because whenever you're doing a nonlinear problem, it's really important to find out whether your solution is converging at each time step. So, okay, I can run that one. What was the other one you said?
Why don't you show the, did you show the .cfg file for that one?
For the step 08?
Yeah.
Okay, so, okay, all right. The very first thing we do is we change the solver. By default, it's a linear solver, but since we're doing a nonlinear rheology, we need to use the nonlinear solver. So that's the biggest difference right there. And then we're going to use adaptive time step, which means that Pilot can change the time step size depending on what's going on with the nonlinear solution. So we're giving it a total time for your simulation of 700 years. We're saying that we don't want to take any time steps that are bigger than 10 years. And this stability factor just controls how much you're willing to diverge from what the safe time step size is. So if you have values less than 1, I believe, it means you're being more dangerous. Is that correct? And if you're having it be more than 1, I believe that you're being more cautious.
Yes, more than 1 will take smaller time steps. So a factor, changes stability factor to a factor of 2 will do half the time step set that you would with a stability.
Okay. Right. Okay. So that is true, that if you increase the stability factor, it takes smaller time steps. And okay, so we're changing our material for the lower crust to power law 3D. And again, you have to give it a spatial database from which we get our material property values. And in this case, we're using what's called a composite database. So that's, we're using 2 databases. One of them is going to contain the elastic property parameters, and the other one is going to contain the power law viscosity parameters. So then that means you have to give it information about each of these. So the ones that are contained in our A database are the regular elastic properties, density, BS, and BP. And we give it our label. And then that's just the same MAT elastic spatial database that's been used in several other problems. Then for the power law properties, this is a long story about why these are the power law properties. You'll have to read the manual. But the parameters are our reference stress, our reference strain rate, and our power law exponent. And so those will be specified in the map power law spatial database. And we're going to interpolate linearly so that those properties can vary, as I believe we have it varying as a function of depth for this problem. And then because we have some more complicated material properties, we're going to have the output provide us information about these materials. So that includes both your elastic properties as well as your power law properties. And then it also, for your data fields, by default we get total strain and stress, but this one also includes a viscous strain state parameter. And so I believe here we're giving velocity boundary conditions on the sides. And actually, okay, should I go through the whole thing with fault rupture and constant creep on the fault?
We did that in our session 1 yesterday morning for the other schedule, but you can go through it. I don't think we have about 10 minutes. But if there are people have questions, speak up.
Yeah. So this is a case where this is a faulting problem where what we're doing is we're specifying periodic rupture on the upper portion of the fault, and we're specifying steady creep on the lower portion of the fault. So we're saying that we have 4 earthquake sources. We have the creep part, and then we have rupture 1, rupture 2, and rupture 3. And so to do that, then we get origin times for each of these. So the creep starts at t equals 0. It starts creeping right away. Earthquake source 1, which is rupture 1, starts at t equals 200 years. Source 2 starts at 400 years, and source 3 starts at 600 years. And then we have to give a slip function for each of our sources. So this is rupture 1. We can use the same final slip rupture, which is just constant slip on a particular portion of the fault. So we can use the same spatial database to give the final rupture. But what's different is that the origin time is different for each of these. So the second rupture looks exactly like the first one, except that it's using a different origin time. And then finally we have our fault creep, which we've already said it, but it has an origin time of 0. And then instead of the rupture slip function, which we had somewhere up here, let's see, or maybe that's the default. Anyway, what we're doing is we're giving it a constant rate slip function. And so that's a particular type of slip function where we have to give it slip rate. And then, so we can look at the spatial databases associated with that. So we have our rupture spatial database, which all it does is at 4 locations it gives the components of slip. And so from the surface down to z equals 2 kilometers, or 2 kilometers, we have 4 meters of slip. And then everything below that, we have 0 slip. Then for the creep spatial database, it's kind of the reverse. In this case, we're giving it slip rates. So in this case, we have no slip at all on the upper portion of the fault. And then below that, we're slipping at, let's see, 2 centimeters per year. So actually, we can just look very quickly at what that looks like. Did I see another question pop up?
Yes. Can we specify a transient?
Transient what?
Like a transient slip, I believe. Like a slow slip event.
Oh, you would have to use a time history to do that.
And so the time history are a step function. There's several slip time histories that have a functional form that are used in forward earthquake simulations, and there's a user specified time history. So you generally, if you're going to do like a slow slip event, I think you'd probably do a user specified slip time history.
Yeah. So I was just going to show what that last problem looks like if we let's see what happens if we just step through. Okay. So this is the problem that we just ran. So this is the creeping part down here, and this is going to be the lock part that's going to slip every so often. Boom, there's our earthquake. We can rescale. And so then it continues on like that, just periodic earthquakes. Now, what we're showing here, we are outputting the domain solution only at certain time steps. I think the ground surface we might be outputting more frequently. So if we just look, at that, maybe only 100. That might be a bit much. So if we just run that one through, you can kind of see what we're doing there. And I think we're pretty close to the end here. Do we have any more questions?
Final call for questions. Doesn't look like we have any more questions.
Okay. All right. In that case, Let's see, what's the next session?
So the next session is solvers. So we're hoping that Matt has made it home from France.
Yeah.
He's supposed to be getting home now. If for some reason he doesn't show up online, then we'll switch the solver session with the fault friction session. So we expect to be discussing solvers in 2 hours. Otherwise, we'll be talking about friction in 2 hours.
So we'll hope for the best.